So last time we defined stress and strain. We defined Hooke's law, linear elastic, nonlinear elastic, and we defined the elastic modulus or Young's modulus. So this time what I'm going to do is just kind of go ahead and basically relate where this elastic modulus comes from. So in this elastic region, it's important to note that we are not displacing rows of atoms or planes of atoms relative to another plane. Like we would in plastic deformation, we're simply stretching bonds. Okay. So you recall this, hopefully this energy plot here as we have two atoms approaching each other. And we said that the atoms will sit down here in this well at an equilibrium separation, R0, and the bond energy E0. So when we start elastically stretching, we're going to be, let's say if we're in tension, we're going to be increasing this equilibrium position, or we're going to be displacing the atoms out of their equilibrium position is what I should say. And then again, and so that would be us walking, say, along this curve. I'm really exaggerating the amount that we would walk along that curve here, but we'd be walking along this curve here as we stretch the sample. And then if we let go, we would come back to this equilibrium position. So another way to kind of see that is to go ahead and take the derivative of this energy with respect to the separation, atomic separation R, okay? And this is proportional to a force. And so that's what we have up here on this top curve. We have the force. Okay? And so if we take a look at the slope down here at our equilibrium position, you can see the slope is 0. So on our force curve, you can see we end up with 0 here. So this equilibrium value we had in the energy curve, the other way to think about it is that that's the location where the sum of the forces is equal to 0. All right. So if that's the case, then if we were to take a look at the slope in here at this equilibrium position where the sum of the forces is 0, then we now have a slope that looks like a force versus separation. In other words, this slope here should be proportional to the elastic modulus. And I'm just going to spell that out so you don't think that E means energy here. So this slope now is proportional to the elastic modulus. It looks like our stress strain curve. Okay. We'd have to go through some conversions to actually get the elastic value because we are in units of force and atomic separation. So we would need to figure out how to come up with an area to make that a stress, and in what way and how we would come about making this a strain value. But what we can do is, at least in a relative sense, we can understand how when we have one material that's very strongly bound, so in the energy, this would be the case for the high, I'm going to try and avoid E here, too many E's. I'll just write bond energy. All right, we talked about bond energy. So the strongly bound case would be where the bond energy is high. This one is the case for the bond energy being low, or at least lower than the red curve here. So a more shallower well on the energy plot. And so if you take a look at those, what you will find is that these slopes at the equilibrium positions is much steeper for the strongly bound sample as compared to the weakly bound sample. And so we would expect the strongly bound sample to have the higher elastic modulus, right, or Young's modulus. So that'll be a high elastic modulus. This other one here then would have the lower elastic modulus. So the modulus is proportional to, again, the derivative of the force with respect to R evaluated at that equilibrium position.